D. Infinity Possibilities Conversation. Today's conversion promises to take us from the comfort of classical certainty to the wild frontiers of quantum probability. Is the universe playing dice, Joseph? That's the title of your piece, and I see you've even brought a dice along. I have to ask, are you implying that nature literally rolls dice behind the scenes of reality?
In a metaphorical sense, yes. For a long time, we believed the universe was like a magnificent, deterministic machine, completely predictable if only we knew all the parts. In classical physics, cause and effect reigned supreme. If you knew the starting conditions, every position, every velocity, you could, in theory, predict exactly what would happen next. It was as if the cosmos were a giant pool table. Hit a cue ball just right, and you know it'll send the 8 ball to the corner pocket every time. Certainty ruled.
A clockwork universe. Predictable, orderly, almost like an enormous cosmic calculator. So, when did the dice come into play? What changed that made us think the universe might be rolling random outcomes?
The turning point came when we peered into the subatomic world, into the tiniest corners of reality. And everything changed. Let me give you a classic example. I call it the problem of the light bulb. Consider a simple light bulb filament. We run electricity through it. Electrons get excited to higher energy levels. Eventually, those electrons drop back down and, in doing so, release a particle of light, a photon. Now, the cause here, the electric field energizing the electron, is well understood and perfectly classical. But here's the profound question. When will that excited electron emit its photon and glow?
Right, we know that it will emit a photon, but not when. Is it truly unpredictable? Couldn't there be some tiny hidden timer or trigger inside the atom deciding the moment?
You'd think so, but nature defies that expectation. Quantum physics says it's fundamentally random. There is no internal clock ticking down, no secret mechanism nudging the electron at a precise moment. All we can say, and this has been confirmed by countless experiments, is that there's a certain probability per unit time for the emission to happen. It might happen in a nanosecond, or the atom might hold on to that energy 1,000 times longer. Nothing forces the exact timing. The electron just decides to spit out that photon whenever, as if by a roll of the dice.
That's incredible. A light bulb flickers whenever it pleases at the microscopic level, yet on the outside we see a steady glow. It sounds almost mischievous of the universe, like it's hiding its randomness behind an average outcome. But let me play devil's advocate. Maybe it's not truly random. Could it be that there are hidden variables, some unknown factors or dice behind the curtain that we simply don't know how to measure yet? Einstein himself hoped for that. He famously refused to believe that God plays dice with the universe.
Ah yes, the great Einstein's quandary. For decades after quantum theory was born, even Einstein and others clung to the hope that the uncertainty was just temporary ignorance. They imagined there might be some secret deterministic code underneath it all, if only we could crack it. But here's the dramatic twist. Bell's theorem and the experiments that followed dealt a crushing blow to that hope. To put it plainly, experiments inspired by John Bell showed that no local hidden variables can explain away quantum randomness. If there were secret dice behind the scenes, they'd have left telltale patterns. They didn't. Nature's randomness passed every test of genuineness. The result? The randomness is real. The universe, at its core, truly behaves like it's rolling quantum dice for certain events.
So Einstein's dream of a secretly ordered universe, gone. The poker-faced universe finally showed its hand, and it was dice all along. This is a huge paradigm shift. Walk me through that shift. How do we reimagine causality itself under quantum thinking?
It's a seismic shift indeed. In the classical view, we had a straightforward chain, cause to effect. One thing leads to another, neat and clean. In the quantum view, the chain gets a new link and a lot more intrigue. Possibility to probability to event. Instead of hard determinism, we have a landscape of possibilities. Think of the universe as performing a constant dance of maybes. And when reality decides, it's like a die roll collapsing those possibilities into one actual outcome. At the quantum level, nature is perpetually tossing this die. Each toss is an event, say, an atom emitting a photon, and the odds of each outcome are set by nature's rules. But the exact result isn't fixed until it happens.
A dance of possibilities. It's poetic and a bit mind-bending. But if everything is so random down there in the quantum realm, how come we experience such certainty up here in everyday life? I flip a light switch and my room light comes on instantly. Nothing random about that to my eyes. Where does this sense of reliability come from, if not determinism?
Excellent question. The key is scale. While single quantum events are unpredictable, when you have zillions of them, their individual quirks average out. This is the realm of the law of large numbers. Take radioactive decay as an example. One radioactive atom might decay in the next second, or maybe not for 1,000,000 years. Who knows? It's inherently unpredictable. But put 1,000,000,000,000 radioactive atoms in a lump, and we can tell you very reliably how much of that lump will decay over a given time. The randomness of each atom washes out into a very steady overall rate. In the same way, a light bulb emits uncountable photons. Their individual emissions might be random, but together they produce a stable glow. We feel certainty at large scales because billions of quantum events are averaging out, fluctuations cancel each other, and outcomes become extremely stable in aggregate. It's not true determinism underneath. It's statistical regularity. What we call certain is really just very high probability. A clockwork universe. Predictable, orderly, almost like an enormous cosmic calculator. So, when did the dice come into play? What changed that made us think the universe might be rolling random outcomes?
So my sense of a solid, predictable world is a bit of an illusion. A numbers game being played by particles. Not clockwork, but crowds of random events smoothing into patterns. Fascinating. And it also sounds a warning. The classical ideal of absolute precision was flawed, wasn't it? We assumed if we just measured everything perfectly, we'd predict perfectly.
Right. Classical thinking carried a huge assumption that we could know initial conditions with infinite precision, and that nature itself had exact values for everything: position, velocity, forces, you name it. But in reality, that perfection is impossible. Every measurement has some error. Initial conditions can never be pinned down to an infinite number of decimal places. And here's the kicker. Even if quantum randomness didn't exist at all, many classical systems would still be effectively unpredictable. Why? Because of chaos.
Chaos, as in the butterfly effect and all that. I've heard of it. Even a deterministic system can be incredibly sensitive to tiny uncertainties. A butterfly flapping its wings in Brazil sets off a tornado in Singapore, metaphorically speaking.
Exactly. Chaos theory shows us determinism without predictability. In certain systems, weather, turbulence, ecosystems, the human brain, the equations might be deterministic, but they're so sensitive that the tiniest unknown detail gets amplified. Today's minute measurement error balloons into a huge deviation next week. So even without quantum randomness, prediction collapses due to sensitivity in chaotic systems. In other words, certainty fails even before quantum effects kick in. Reality has many ways to surprise us.
So, either way, quantum indeterminacy or classical chaos, the message is we can't predict everything with absolute certainty. That's humbling. It tells us there's a limit to control. But it's not all gloom and throwing up our hands, is it? Because your article suggests a shift from control to design. What does that mean?
This is perhaps the most empowering lesson in all of this. Quantum mechanics teaches where control ends and design begins. We cannot control exact events. We can't demand a particular electron to emit now, or the weather to obey our plan on Tuesday. But we can control conditions. We can set things up in a way that shapes the probabilities of outcomes. Think of it like loading the dice. You can't force a 6 on any single roll, but you can weight the die so 6s come up more often on average. In life and engineering, this translates to designing systems that are robust to randomness and even exploit it. We stop trying to force outcomes and start engineering likelihoods.
That sounds powerful and pragmatic. Instead of chasing certainty, we manage probabilities. Can you give some examples of how this idea extends beyond physics? I mean, it's a philosophy of thinking, isn't it?
Absolutely. This shift in mindset has broad implications. In engineering, for instance, we design with safety factors and redundancies because we know components can fail at random. We can't predict which part will fail when, but we can ensure the bridge or airplane stays up by planning for probabilities. In economics and finance, traders and policymakers embrace uncertainty by hedging risks. They know markets have random swings, so they structure investments to withstand or even take advantage of that volatility. Even decision-making in everyday life changes. Instead of saying, "This will happen for sure," a quantum thinker asks, "What are the possible outcomes, and how likely is each?" That leads to better planning. We see this probabilistic approach in fields like biology. Think about genetic mutations and evolution. Inherently random, yet yielding robust life. In AI, which often deals in probabilistic predictions. Really everywhere. Once you accept that uncertainty is fundamental, you start to make decisions differently. You become a designer of outcomes, not a controller.
It's like a renaissance in thought, from Newton's clockwork precision to Darwin's and Maxwell's probabilities. But I suspect many people are uncomfortable with uncertainty. They think of it as ignorance or a flaw in our knowledge. How do you reframe uncertainty so it doesn't sound like throwing up your hands in defeat?
By recognizing that uncertainty is not a mistake or a weakness, but a feature. It's not that we're too stupid to find the hidden gear. The gear isn't there. Uncertainty is woven into the fabric of reality. I often tell people, it's not ignorance, not failure, not just noise. It's a built-in feature of the universe. When you truly grasp that, it's liberating. Instead of fighting uncertainty, you work with it. You plan probabilistically. You consider a range of outcomes rather than just one. You hedge your risks, meaning you prepare for more than one possibility. You design resilience into systems so they can handle surprises. This is exactly what modern fields do. Finance, artificial intelligence, risk engineering. They all embrace uncertainty, modeling probabilities to make reliable choices. It's not about giving up on understanding. It's about understanding differently.
This is a profound shift. So instead of asking the old question, what will happen, we should be asking,
what can happen, and how likely is each possibility? Exactly. That's the quintessential quantum thinking question. When you start framing problems that way, you become a better planner, a sharper scientist or engineer, even a wiser decision maker. You stop expecting certainty where none exists and start focusing on probabilities and outcomes you can influence.
It's poetic and practical. A simple change in question, but it opens up a whole new way of approaching everything from science to daily life. He turns the die in his fingers, then lets it roll one final time. You've certainly given me, and our audience, a lot to think about. The universe may be rolling dice, but thanks to this conversation, I feel we've learned how to watch the game and even play along wisely.
Well said. Embracing the dice doesn't mean we're helpless. It means we become savvy gamblers in a sense, understanding the odds, respecting the uncertainty, and making our moves with that knowledge in mind. That's the heart of quantum thinking, accepting the cosmic dice roll and designing our world around it.
And that acceptance, that shift from demanding certainty to managing probability, might just make us all better at what we do, be it science, engineering, or just living our everyday lives with a bit more grace for the unpredictable. Thank you for this illuminating discussion.
Thank you, Natalie Dawson. It's been a pleasure rolling the dice together on these ideas.